Okay, good morning. So today we continue for some non-ideal effects or some additional for the MOSFET. The first one we will discuss is related to the mobility variations. So when we try to derive the IV relationship, actually we always assume that the mobility was a constant. So that's trying to simplify our questions. But in reality, actually the mobility is not a constant, and they could be possible for two reasons. The first one is we have to consider there is a variation in mobility when we apply the different gate voltage. This is because the ones we apply the positive gate bias here. So ideally we will, once we apply the gate bias larger than threshold voltage, so we should start to have the inversion electrons in the channel, and then we apply the positive drain bias. So therefore in this case we consider the electron is actually flow from the source to the drain side because of positive drain bias. But in reality, once we apply the large enough gate bias, and it could be this electron will be also be able to attract to the dielectric. This is because we also apply the gate bias. And therefore, we also have to consider that the mobility might be influenced by the gate bias. And in this case, we start to see there's a variation in the mobility once we apply the different gate bias. So that's the first thing we had to be considered. And the second one is the mobility variation is that the effective carrier mobility decrease as a carrier approach to the velocity saturation limit. So once actually we cannot expect that all of our carrier can be moved very fast. As long as we increase the drain bias, it will always will reach to a certain saturation limit, and that's we call as a velocity saturation. So usually, once we consider the velocity saturation, we have the plot roughly like in this way. So we have the x-axis, which will be the electric field, and then the y-axis, which will be the mobility. And therefore we often to see that in the beginning is a linear dependency, but at a certain moment we can start to foresee there's a velocity saturation. So this is a velocity saturation. So that's why the mobility actually will have this saturation effect because of due to the this kind of phenomena. So in the next slide, we will also talk a little bit more about the velocity saturation. So the carrier velocity increase until the current, ideal current is attained. However, we have seen that the carrier velocity saturate with increasing electric field. velocity saturation will become more prominent in short channel device. Seems the corresponding horizontal electric field is generally large because the short channel it means that so that means our channel length is small. So once our channel length is small, actually our electric field is larger. So the velocity saturation will occur when the horizontal electric field is approximately reach to this kind of level. So if we have the VDS operate at 5 volt in a device with a channel length of 1 micrometer, the average electric field is equal to this value, and velocity saturation is very likely to be occur in a short channel device. And once we have the velocity saturation, we also have to consider the different current equation. So this is the equation once the device has reached in the case of velocity saturation. And here is some of the case with respect to the different semiconductor materials. So as I have already drawn before, that the x-axis will be the electric field, and then y-axis will be the carrier drift velocity. So we can see in the case of electrons, in the case of silicon, so these are the case for silicon. For example, if you look at for the case in the electrons, so we can see in the beginning it's linear increase as we increase the electric field. However, once the electric field is larger enough, we can start to see the saturations happens here. And therefore, if you consider the current equation, so in the previous, when we discussed the IV calculation, we assume this is a constant mobility. So we have the IV curve like in this way. This is under the constant. But once we consider the velocity saturation, so we can start to see that actually the current cannot increase fast as we expect. So this is one example. You can see this is a case under the velocity saturation. This is at 5 volt, and there's a huge difference between the constant mobility and also the case with the velocity saturations. And next interesting phenomenon is we also call as a ballistic transport. So the average drift velocity is a function of mean time between the collisions. Or the mean distance between the scattering event. So that means in the long channel device, the channel length usually is much longer than the mean distance between the collision. So the average carrier drift velocity exists. But once we reduce the channel length, the mean distance between collision might become same, almost comparable to the channel length. And therefore, the previous analysis might not be valid here. And this is because of the one you can expect once you have the electron moving in the channel, it definitely will have certain collision with other, for example, the defect or other atoms here. And once this mean distance between the collision, which is larger than channel length, and that's because of our channel length is very small, then in this case we can consider that the electron moving in the channel didn't have any collisions events anymore, and that's why we call this as a ballistic transport. So in the channel length is further reduced. So when our channel length is smaller than our mean distance between the collisions, so the L is the mean distance between the collisions. For example, if we assume our 1 micrometer will be the mean distance between the collisions, and right now if we fabricate the device with only channel length of 50 nanometer, and that means actually our 50 nanometer is much smaller than our mean distance between the collision. And in this case, we can consider that when the electron traveling in the channel, the electron won't face any collisions process, and this is the case we call as a ballistic transport. So this is exactly this sentence trying to explain. If the channel length is further reduced, so when our channel length is smaller than our mean distance between the collisions, and large fraction of the carriers could travel from source to drain, but right now without experience the scattering event. And in this case, we call this as a ballistic transport. And the next one we will discuss is related to the scaling. So as you know, the semiconductor, part of the semiconductor device, if we try to push for the advanced technology nodes, one of the targets is trying to do the scaling. And however, actually when we talk about scaling, there are different kinds of the definition for this scaling. And in this slide, we just show like the definition for scaling from very early time that we consider as a constant field scaling. So the principle of a constant field scaling is that the device dimension and device voltage to be scaled such that the electric field remains constant. So that's why in the early time when people try to propose what would be the possible rule or possible roadmap for the scaling, the first idea come to our mind is that we have to fix the electric field. So we want to do the constant field scaling, try to reduce dimension and reduce the voltage that can make sure our electric field remains constant here. So this gives a certain idea. So for example, if we have the device like here, this is a TX or Oxide thickness, and this is our channel length, and this is our junction depth here. And in the early time, we consider that there's constant factors here, try to reduce to the, in the sense that we can maintain the same electric field. So if we try to put some number, which can be, for example, in the old technology, the VG might be applied at the 5 volt here, and we have a 10 nanometer oxide thickness here, and we have a channel length 1 micrometer, and our doping concentration can be 10 to 7, so that can be in the original old design. But right now, if we do the scaling, we will apply the K factor here. For example, let's assume our K factor is 0.1. So that means if we move to the next generation to keep the same electric field, how we need to do is we have to make sure that our voltage bias cannot be higher than 0.5 volt. In this case, because we fix the electric field, and that means right now our oxide thickness can only have 1 nanometer. So that's a concept of constant field scaling, and for sure this will be equal to 100 nanometer as well, because this is equal to KL. Still, like the we put the 0.1 factors here, and then the doping right now is changed, which this is a doping. So now the dopings become 10 to 18. So that's the first idea to have the scaling rule that based on the constant field. But if you try to, but the reason that in the end we cannot follow the constant electric field scaling is because you can realize that the dielectric here is almost reached to the limitation for the 1 nanometer here if we continue to do this kind of constant field. And the 1 nanometer dielectric actually will suffer a lot of reliability issues, including the very high gauge current, very weak lifetime for this dielectric. So therefore, after a certain moment, people realize that we cannot use this rule anymore. But this rule still gives us a good sense that what's our goals to try to do the scaling. So typical, it's around 0.7 for per generation for a given technology. So that means that each generation we will put the 0.7. We put the 0.7 factors in the dielectric thickness, in the channel length, and so on and so on. And the next is we have to discuss for sure that once we do the scaling, the most critical challenge we will have. First one is a short channel effect here, and this is the reason that why we have to move on from the two-dimensional transistor for the 2D structure to until become the 3D like the FinFET. We move from the planar MOSFET for the 3D kind of like a FinFET. So the space charge region at the source and drain extending to the channel region, but occupy only a small fraction of the entire channel range here. And this is in the case with the long channel. So you can see in the bottom left graph here, this is our channel length is here. And as you know, once we consider the source and drain, let's definitely we have to take into account the PN junction in the source side and the drain side. So without any given bias, it's already there's a space charge region, there's a depletion region in the source and drain side here. So right now this is the space charge width in the source side and the drain side. But because our channel length is much longer, so that means the depletion region, which is much smaller than our channel length. So in this case, this is long channel. Because our space charge region is much smaller than channel length, the gate voltage will control essentially all the space charge into the channel region and the inversion. So you can see this is our gate voltage applied at here. And because right now these are very small, so the channel charge here is almost dominated by our gate voltage here. So this inversion channel is mainly controlled by the gate. Because right now our space charge in the source drain are extremely small compared to the whole channel length. So therefore we won't face any short channel effect at this moment. But now you can expect that once we continue to do the scaling of the channel length, there's a moment that our space charge region in the source drain, the width of this space charge region will almost comparable to our channel length, sometimes even larger. It's almost occupied for our whole channels. So this is the one that we have to worry about. As the channel length decreases, the fraction of the charge in the channel region controlled by the gate decrease. Why decrease? So you can see right now the channel length is become smaller here, and we still have to consider this part. This part is our space charge region, is a depletion width due to the source side PN junction and drain side PN junction here. But now the gate voltage, once we apply the gate voltage, and we can only modulate the small portion of the charge in the channel here. So the inversion cannot be fully controlled by the gate at this moment. At this moment. So right now your gate, you can assume that you have, this is for example like 1 micrometer, and you have a 1/3, and 1/3 is total will be the 2/3 is dominated by the depletion width, and only 1/3 micrometer can be controlled by the gate here, and therefore we will start to suffer in the short channel effect. One of the issues for the short channel effect is that you have to realize that we are not only apply the gate voltage, but also we will apply the drain voltage here. So once we increase the drain voltage, you can expect this depletion width will further extend. So now we will start to face the current will be increased even we don't apply the gate voltage, because this drain voltage will continue increase, so this will be further extension, and there's a possibility that the electron can start to flow from source to the drain without go through in the channel. So right now, if you try to apply the gate voltage equal to 0 volt, you cannot still turn off the channel, because right now the electron can start to move from the depletion region from the source to drain side here. So that's a major problem for the short channel effect here. So here is some of the further calculation for the short channel effect. The idea is that we actually will find out that our threshold voltage actually can be influenced from the different channel lengths here, and therefore we can calculate the delta VT, which is threshold voltage under the short channel minus the threshold voltage under the long channel. So this is a nice evidence to indicate the short channel effect. So if you look at the literature, you will find out that in most of the literature, if they want to prove that there's a short channel effect, it's always trying to plot the delta VT versus the channel length. So here is an example here. So try to calculate threshold voltage shift due to the short channel effect here, and you can look at the example by yourself. That give you some of ideas, and then the result is that once you have this short channel effect here, then you will see the delta VT shift, which will be the negative shift. So you will have the negative threshold voltage shift here. And here is a more clear evidence for the short channel effect here, because you can right now to see once we decrease the channel length here, we can clearly see our delta VTH. Our VTH is become negative here, and that is one of the strong evidence for short channel effect. And sometimes we consider, so the channel length decrease, we can clearly see the threshold voltage decrease, and this is in the literature we also call this as a threshold voltage roll-off. So sometimes you will also see this kind of the term in the literature when we try to discuss short channel effect here. So this is just a different literature. So this is this one, and this also another literature try to describe the short channel effect here. And in this one you can see this VDS dependency. So this is VDS at 0.125 volt, and this is VDS at 4 volt here. So larger VTS, usually we will also see the more obvious short channel effect, and this is because we have the extension of the depletion region. And in addition to the short channel effect, there is also the concept called as a narrow channel effect, and this is because of there is a additional space charge region at each end of the channel width. For example, if this is L, this is L, that means you have to imagine this is the channel length. So this is a dimension that usually we shown in here, L. So this is L, and this is usually the W. But now we will try to look at from another angle here. So now this is L, and this is W, the channel width here. So the additional charge is controlled by the gate voltage, but not including when we try to calculate the ideal threshold voltage here. So this is here, this one. XDT, that's an additional space charge width. So in this case, we will actually find out that there's also influence in our threshold voltage as shown in here. That's why we need to have the space this influence on the threshold voltage. We will distribute the gradient the midterm today, and I think that most of the suggestion, and some of you actually give the suggestion that I should focus on more on the calculations in the lectures, but I have to be fair with that. It's not possible to include too many explanation of the calculation in the lecture, because I believe that the physics concept is more realistic to address the real issue. And the reason why that the midterm and also homework has to in the question that list all of the calculation, because I need to have the fair way to evaluate the score. If all of the question is only like a Q&A, it's very general, like physics-based question without any calculation, it's not possible to evaluate everyone's score in the very fair way. So that's why the question has to be designed in this way, because in the end you still need to have the very good way to evaluate the score for everyone here. But just have to remember that in reality that all this equation right now can be solved by the software. If you try to look at for the literature in the semiconductor, or you try to address the real world issue, actually it's very less often that you need to use your hand calculation to derive something. For sure, there's a part of the work is related to the analytical modeling, related to the calculation, try to derive something. But I would say right now, more than like 80% of the work can be replaced by the computer. But the physics is not still will be the most important, because anyhow, once you derive something, try to calculate some number, you still have to understand that all these number makes sense or not, is really fit into the physics model, is really fit to the possibility to address the issues. So don't be misunderstood that the focus of this class is calculation. Actually, it's more related to physics sense here. And also, one more thing I want to remind us that this is a course for the graduation class. So the graduation class is required that everyone to be independently do more exercise at your home, to do more for thinking, not expect that everything can be lectured in the class. So we are not the undergraduate class, we are not the high school class. I know for the Taiwanese education in the past, we used to try to have the mindset that they want to learn more calculation, try to solve more mathematical equation in a very fast way, in an efficient way, try to understand every calculation. But it works fine for the undergraduate or even for the high school. But in the realities, actually, we don't really use this equation. For me, I didn't remember any equation, but what actually in my mind is all about this physics knowledge to solve the issues. But in the class, still need, because I need a way, the certain good way to fair evaluate the everyone score, because in the end I need to have the one score that have the pretty standard criteria for everyone. But if we only have this, like the Q&A, like some of the explanation question, is not be able to have the fair evaluations. Okay, so this is some of the result for narrow channel effects here. So you can see that there's a dependency of the width here. So you can see the threshold voltage is increased once our channel width is decreased. So this is a summary that between the short channel effect and then also the narrow channel effects here. And to be honest, I think the short channel effect is much important, because we actually trying to fabricate the device with a smaller channel length here. So sometimes we also call this short channel effect as a SCE. So that's a term very often used to describe this phenomenon. So in general, when we talk about the short channel effect, there's two important outcomes. The first one is we can clearly see our threshold voltage decrease, and second one is we can see our leakage current increase. And that's why in the very early lectures here, in the first lecture, we have discussed that how do we try to reduce of leakage current, and then the proposed structure will be the, for example, SOI or FinFET. And another thing we have to also worry about is that there is an issue related to oxide breakdown here. So when we try to talk about the IV current here, we always assume that there is no actually the current will flow in the dielectric, but which is not true. So if you now look at the MOSFET, we have the dielectric. Here, so once we apply the gate bias, actually, for sure, that first one we will start to form the inversion electrons in the channel. And actually, we can also expect that this inversion charge, this electron, can be possibly flow to the top of the gate metal. And because of the under the quantum mechanics, we already discussed what we call as a tunneling. So in this sense, if you try to look at the band diagram here, so in the beginning, we have the oxide semiconductor band diagram like this one, but under the positive gate bias. So now we will start to have the band bending here, and also our dielectric will be changed in this way. This is under the positive gate bias here, and therefore we can start to expect there's an electron here. So electrons not only flow to the drain side, but also be possibly flow to the gate, and in the end reach to the gate metal. So that's one of the reasons that we have the the gate leakage current here. So if you look at the real electrical measurement result here, so this is a gate current versus the gate voltage here. So you will very often to see actually there's a certain amount of the gate current can be obviously observed. And this gate current is certainly depends on our gate bias. So that means higher gate bias we always has a higher gate current. And once reached to the certain limitation, you will start to foresee this suddenly increase of the gate current. That's we usually call this as a dielectric breakdown. And this is a phenomenon because right now the dielectric lose the insulating property. So that means our dielectric is not the dielectric anymore. It's become the conductive material. That's why you will start to see this very high leakage current. And we just call this as a breakdown. So if the electric field in the oxide becomes larger enough, breakdown can occur, which can lead to the half values here. So that means right now if we have this kind of phenomena, actually our device cannot, our dielectric is not insulating anymore, and then we can start to see the completely failure for our device here. And in addition to the gate current versus voltage here, we also have to be worried about that there is issues related to the gate current versus time. So similarly, we can also expect that with a certain fixed bias here, for example, in this graph might be bias, we just give the constant bias of the VG at the 10 volt here. So if you try to look at this graph, at the 10 volt, our device should be still, our dielectric still should be good enough because the leak current is very low. Here it is 10 to minus 10. So that means ideally bias at the 10 volt should not give us a problem. But in reality is that once you bias as longer enough, we will still face, after a certain moment, have the breakdown occur here. And this is related to the time. So that's why we call this as a time-dependent dielectric breakdown. And sometimes we just call this as a TDDB here. So the TDDB is one of the major reliability challenges in all kinds of semiconductor device, no matter what you are working on, no matter for front end, back end, whatever, as long as you have a structure related to the dielectric metal or dielectric semiconductor, you always will face the TDDB issue here. And in this class, we won't talk about the TDDB too much, but in my another class related to reliability, we will talk about the TDDB in a very comprehensive way from the fundamental until very advanced knowledge, also including lifetime fitting. Okay, so that's one of the issues for breakdown. Another issue is related to the average breakdown. So if you look at this is schematic for the MOSFET in the drain side here. So if our drain voltage is larger enough, we can start to foresee there's a average breakdown can be happen. And this is because once we apply the large VD, this is a reverse PN junction here. In the previous lecture, we already mentioned that if we look at the single IV characteristic for PN junction, we have the forward characteristic, like in this way. But also, in terms of reverse, after a certain moment, we start to see the breakdown. And this is because due to the average breakdown. But also, similarly, this is under the reverse PN. But when we operate our MOSFET under the positive VD, it's actually reverse our PN junction. So we can expect the very similar phenomenon can be happen. This is IDVD, but now it is under the large VD. So after as the VD is larger enough, this is case at the VG 0 volt here. And as long as the VD large enough, we can also expect there's an average breakdown. So basically, once you understand the PN junction, lots of things in the MOSFET can be easily understood as well. And another phenomenon we will consider is called the punch-through effect here. So the punch-through effect is mainly happen during the short channel device. So this is because we actually already mentioned before, if we consider the MOSFET so we all know in the MOSFET there's already the depletion region will be formed in the source side and the drain side. So this is our depletion region. And right now, if we apply the VD, which is larger enough, the depletion region will further extend. Will become like in this way. So you can see now our increase our depletion region. But right now, this is still under the case of VG 0 volt here. So that means there's no electrons in the channel, but our depletion region is already extending to the other side. So therefore, this is a case, that's what we call as a punch through. So in this case, right now, the electrons can start to flow from source to the drain side without going in the channel. So that's why we consider this is a punch through due to the extension of the depletion region. So punch through is a condition which the drain to substrate space charge region extend completely across the channel region to the source substrate space charge region here. So what this text talking about, drain to substrate space charge region is here, and source to substrate space charge region is here. So in this case, this space charge region extend completely across the channel region and touch the source side depletion region. In this situation, the barrier between the source and drain is completely eliminated, and the very large drain current can exist. So ideally, if you look at the band diagram from here, source to the channel, source to a drain, so we have this is a N plus P N plus here. So we have the loss of electrons here. But right now, the electron cannot flow to the right hand side because of due to the barrier here. But once we have large drain bias here, so the drain bias will start to pull down the band diagram here. Now you see the barrier here is become smaller, and once the barriers become smaller, there's a chance the electron can tunnel from the source to the drain side, even there's no gate bias here. So that's why you can see this is generally the curve at the VG at the 0 volt. So you can see even at the VG 0 volt, as long as the drain bias is large enough, the current is increased. And for sure, once we increase the gate bias, the current will increase much faster. And the most critical problem for this case is not only we have very high lead current at the VG 0 volt, but also we don't have the saturation characteristic. So now we will got the issues because we don't have the obvious saturation characteristic, and that's gives the issue that we cannot very successfully model or predict this kind of a transistor characteristic. So in general, in the case of the punch through, there's two issues. The first one is high leakage current. At VG at the 0 volt, and second one is we don't have the saturation characteristic. Okay, so that's the phenomenon that we call as a punch-through effect. And the next one is also the very often used design that we call as a lightly doped drain. So the junction breakdown voltage is function of the maximum electric field. So as the channel length becomes smaller, the bias voltage might not be scaled down accordingly. So the junction electric fields become larger here. And as the electric field increase, near average breakdown and near punch through effects become more serious here. So we will have the higher chance to have the average breakdown, higher chance to have the punch through effect. And therefore, once the geometry is scaled down, the parasitic bipolar device become more dominant and breakdown effects are enhanced. So in general, what all these texts means that once we do the scaling, we will have a serious average breakdown can be happen. We can expect a higher chance for the punch through effect here. So therefore, we have to do the modify for our transistor design. And one thing we are using very often is called the lightly doped drain here, which means that we will design the N- in the drain side or source side, and that's we call as a LDD. So this LDD is very widely often used in the semiconductor device because that's very effectively to reduce the peak electric field in the drain side. just one more comment, like usually we will use this is x coordinate of electric field versus the position along the surface. So you can see this is an electric field, and this is conventional. Conventional, we have a high electric field here, and if we consider the LDD, then we can see this is a low electric field in the drain side. This is because of due to LDD. So the conclusion is that once we employ this LDD design here, we can reduce the peak electric field in the drain side. And once we reduce the peak electric field in drain side, that can give us an advantage to avoid the average breakdown, to avoid the many issues here. And also, we will be interested to consider how we can further to tune our threshold voltage. And one possibility is by using the ion implantation. So as you know, probably I think most of you in this class have been already familiar with the process. So you all know that once we use the ion implantation, we can intentionally to put some additional species or additional concentration in a certain place. So several factors such as fixed oxide charge, metal semiconductor wall function, oxide thickness, and semiconductor doping, that all can influence the threshold voltage here. And we can also use the ion implantation to change and adjust the substrate doping. So that's the purpose we can adjust the substrate doping near the oxide semiconductor, and then we can further to tune our threshold voltage here. So this is an example that we have this one. This is one example that we try to implant the different species in the service channel here. Then we can start to tune our threshold voltage here. So this is in the end we can have this equation. We can find out our additional threshold voltage is actually influenced by this additional acceptor outcomes due to the implant into the p-type substrate here. So in this case, we can start to see that the threshold voltage can be manipulated after the different kind of implantations. And the last additional non-ideal effect is all related to still related to certain reliability, is what we call the hard electron effects here. So as the electric field in the drain space charge region increase, the electron hole pairs can be generated by the impact ionization here. So we can expect that once the VD is increased here, so this is under the condition we already turn on our transistor, but at the meantime we apply the large VDS here. So once we have large VDS here, so we can start to expect less impact ionization can be happen in this region. This generated electron will be swept to the drain, and generated hole will be swept into the N substrate as well. So that means this electron can be swept to the drain, or this hole can be swept to the substrate. But some of the electrons generated in the space charge region are attracted to the oxide, because right now we apply the VGS. So therefore, some of these can be attracted to the gate side here. And these generated electrons have the energy far greater than thermal equilibrium value. That's why we call this as a high electron. So the reason is we call high electron, just you expect that you try to give the lot of energy for this electron, because this is under the condition that we have the higher gate bias and higher drain bias. So the carrier here is actually again a lot of energy. So the electron in this region are very excited, so they will want to move in the other place. So that's why we call this as a hot electron here. So the energetic electron will cross the silicon dioxide interface and then generates additional interface state. So that means once this electron moving to the top, actually will damage this interface. So therefore, lots of interface state can be generated at this location. So the proper cause of interface state generation is due to the breaking up of silicon hydrogen bond. So that's the case in the silicon. And dangling silicon bond is produced, which acts as interface state. And the charge trapping in the interface state causes a shift in the threshold voltage here. So in overall, the issue is that once we have the hot electrons degradations, we have the high VD. We also have the high VG at here. And now we can expect there's a lots of the interface state can be happens or generated in the drain side here. And this interface state will cause electron trapping. So therefore, there is a trapping issue. And this trapping, the charge trapping in interface causes a shift in the threshold voltage, and in the end will cause additional surface scattering and also reduce mobility here. So that's the issue of a high electron effect here. So here I just use one slide, but actually if you try to dig into the deeper and deeper, you will find out that the high electron effect has been already studied for more than 20 or 30 years, but nowadays still as one of the reliability challenges, especially in the case of a scaling device. Why the issue is a problem in the scaling device? Because right now, once we do the scaling, actually the electric field here is higher, and once the electric field is higher, it's more obvious to have the chance to have the implantation and have the high electron effect here. So in general, once we do the scaling, we actually will see these certain reliability issues, not only for the high electron effect, but also, for example, for the gate dielectric, TDP, or whatever. Actually, all the scaling is certainly accelerate these reliability issues as well. Okay, so that's end of our MOSFET here. Now we move to the bipolar junction transistor. So the BJT is another kind of device that has a completely different operations compared to MOSFET. To be honest, sometimes it's getting more complicated because the BJT considers the operation of the minority of majority carrier. So now you have to back to the mindset like a PN junction, because that is exactly the device that connected to PN junction. So the full name for this is called a bipolar junction transistor, and that we call as a BJT. So basic schematic for the BJT is still as a 3-terminal device, but now it consider the structure like this. So we have the first most common is we call the NPN. So we have the emitter in the left hand side, we have the collector in the right hand side, and usually we also have the base region. We have the base connection in the middle side here, and in generally it's considered as a NPN, this kind of a bipolar, but in reality we still will try to make the doping a little bit different. So usually we prefer the N++ in the N side, the P+ in the base side, and then the N in the collector side here. And here you can find out that there are 2 different PN junctions. The one is between this one. There's a 1 PN junction here. This is usually we call as a BE junction, the junction between the base and emitter. And also another one is we call as the BC junction, the PN junction between the base and collector. So this is a bipolar transistor, the very basic one that we use for the NPN BJT here. If you look at the circuit symbol, that's look like in this way. So we have the base, we have the collector, we have the emitter here. So this is typical for the NPN BJT. For sure, we can also reverse the way as we call as a PNP BJT. So in the case of a PNP, we have the emitter still the same. We have the collector, and we have the base. And also in this, we consider this is a P++, N plus P here. And then the circuit symbol for this one, we have the base, collector, and emitter here. And the next one is just showing the realistic of the carrier doping here. So as I say here, we actually consider we have the N++, P+, and N here. So we have this is N++, P+, and N, because the y-axis is ND minus NA. So when we talk about the bipolar transistor actions, actually there are 4 different operation regions here. So operation regions depends on the forward or reverse bias of all these junctions. Because right now we have 2 junctions here, so that we have to consider the VCB, the collector and base junction, and also the VBE, the base, and also the emitter here. So therefore we have the 4 different regions here. The first one will be very interesting is the forward active. So the forward active is a region that the base emitter is forward bias and base collector is reverse bias. So that will be in this region. This is a forward bias or forward active. Also, on the other hand, we also have very interesting, another one is both BE and BC are forward bias, which will be in this part. That we call as a saturation region. And therefore, we can also have the region that both PN junction are reverse bias, or just completely reverse operation compared to the forward active. That we call as a inverse active here. So if you look at this, is a typical operation schematic for the NPN here. So basically we will have the base current here. So you have to understand that the BJT is a current drive. It's a transistor determined by the base current. So we use the base current to turn on our device. So therefore, if we try to plot the typical IV curve here, now it's actually we are interested in the collector current versus the VCE here, the collector emitter voltage. So that's IC VCE here. And how do we modulate this transistor? We still have very similar characteristics like the MOSFET. The only things, the major difference is that right now we actually modulate the transistor by using the base current, not gate voltage. So if you still look back to the MOSFET, you will find out that when we plot the IDVD, we actually modulate the gate voltage. But right now, we are consider the BJT is that we look at the IC versus VCE, but now we modulate the base current as shown here. So in the typical output characteristic for the MOSFET and BJT is very similar because this curve still very similar like the MOSFET. The only thing difference right now in the later part is we have to explain why the curve it looks like here, because the detailed operation that can cause this curve is different from the MOSFET. Okay, so we will take a break, 10 minutes, we'll come back 10 minutes later.
哎，可是我们刚刚不是看到一个镜头，哎，就是我跟你说，哎，有点小泡到，其实掉，就是因为我们看过去，其实。
我作业写在一起，可以一起讲。
记在一起什么意思？
就是我6、7的作业是印在一起。
哦，应该可以，应该。
这样子。
OK。哦，对，就是。
应该是这么讲。我是共同。
我知道，他没有跟我讲。对，所以就变成我应该是用书我签这边，应该只要这一张就好。对，然后我会签完之后，我再一起直接交过去，我帮你们去找夏老师。那是就现在还没有。对，Student ID 现在也没有。
好像有了。
啊，有吗？有吗 ？OK， 好。 啊，对，期末考时间应该会，因为那天原本是放假，对，上面表定可能应该会延一个礼拜，对，可以吗？
没有，我去确认一下，因
对对
为我要买票。
哦，OK，好，我最慢在下礼拜，你要先买那个回家票。
没有，不是来的票。
来的票是不是？如果说我下礼拜再那样子会太晚。好，我是下礼拜前会。对。Okay, so we will continue. And before continue, just one thing I want to discuss. So right now, today is 5:20. And I expect to finish all the class in the next week. So that will be the 5:27. So in the next week, we should be able to finish the BJT and also the JFET. And we won't have the class in the beginning of June because I will be abroad for the conference, so we will have no class here. And fortunately, the June 10th, that will be the holiday, which is 端午节, so which should be the holiday. And therefore, I still need to arrange one more time for the final exam. So I propose that we can have the exam in here, Monday morning. So will that be fine with everyone? Or otherwise, we have to arrange some other times in the evening between the June 10th. In that week, we have to arrange the final exam in the evening, or just exactly we shift 1 week further. So you can think about this, but we can make the decision, make the final announcement next week. But I think likely, probably, we will have the final exam here. But if you have any questions or any conflict with your own schedule, you can let me know first, and I can still try to shift the final exam to the other days. Okay. Okay, so in the previous slide, we talked about the basic schematic for the BJT, but actually this is a real device schematic. So in the real device schematic, actually the base is designed. We have the NPN here, and then we still have to find a way to connect the base. So therefore, you will have this design that allows us to connect to the base side. And also this will be the emitter, so each part will be the one NPN BJT. Okay, so now we'll move to the further analysis of the BJT, try to understand the operation physics here. And the most important is that we will focus on the minority carrier distribution. And the reason why we have to focus on minority carrier is that if you look back to the PN junction,
we have already derived that the current transport in p-n junction is dominated by the minority carrier. So that's why we will focus on the minority carrier distribution rather than majority carrier, because we already get similar experience from the p-n junctions here. So the first one, we have to analyze the minority carrier distribution in the case of the forward active, which is forward bias in the base emitter junction and reverse bias in the base collector here. And in this analysis, you need to have a little bit patience because of this is pretty unique in the BJT, and sometimes it's easy to be lost because of the complicated for this drawing here. So we first to draw the emitter and base and collector. And right now, we are considered in the different region where we have a different coordinate here. So we have this one. This is a junction between the base and emitter. We also have to consider the junction between the base and emitter. So sorry, this is a junction between the base and collector, and this is junction between the base and emitter here. And we try to give the certain coordinate here. So we have here is x prime prime equal to 0, and this is x prime x equal to 0, and this is x equal to xb. So that's a base width. And we also have this one. So from this definition, so the direction is shown me here. So that's a direction for these three different coordinations here. And now we have to consider that in reality, in here we consider for the case of the NPN, but actually we consider is a case of N plus plus, P plus, and N here. And if you still remember, once this is N plus plus, and the minority carrier concentration is PE0. This is a static minority carrier concentration, right? So because this P plus plus times this one will be equal to the Ni squared. So if you have a higher majority carrier contribution, you have a lower minority carrier concentration here. So in here, which is a minority carrier in the emitter, which is a hole. So that's why we call this as a PE0. 0 means a static, E is emitter, and P is because this is a minority carrier in the emitter, which is a hole here. And also we have the NB0 because the minority carrier is an electron. And we have the PC0, that's a minority carrier in the collector, which are the holes here. And now the next one is we have to draw the distribution here. So distribution has been drawn in the way that you need to little bit recall what our drawing in the p-n junction. So if you look at the typical case of p-n junction, we already draw our majority carrier distribution will be like here. If we only have a single p-n junction, right? So similarly, we can expect we can have this one. This is a majority carrier distribution, a minority carrier distribution, PE, with respect to the X prime space here. So that's a minority carrier distribution in the emitter side. But also in the base side, if we only consider this p-n junction, we can expect that should be like in this way. But right now we have the two p-n junction, and at this moment this is a reverse bias. So reverse bias means that at this point we should not have any carrier concentration. So therefore this will change the minority carrier concentration, become like in this way. It needs to be 0 at this place. So once again, just reminder that in a typical p-n junction we have here back to the static concentration. But right now this is reverse bias, so it definitely need to be 0 at this place. So we have very dramatic decrease of a minority carrier in the base region here. And right now this is reverse bias, so therefore we can expect it's also starting from 0, but now you will still go back to the steady state. So that's a PC minority carrier in the collector side with respect to the X prime coordinates here. So that's the case under the forward active. It's not easy to be understood, to be honest. So again, let's just look at this one. This is typical p-n junction. So as I already said, if you look back to the minority distribution in the p-n junction, we already expect the result like in this one. Now the only difference here is because right now this is a reverse bias. As reverse bias means that at this junction edge, the concentration needs to be 0. So this will force your minority carrier concentration decrease until 0 at this point. And also, in the beginning, the steady state is here, but the thermal equilibrium is here. But now you will back to the 0 here. So that's a case under the forward active here. And now if we look at for saturation, so still the same, we have the emitter. We have the base. We have the collector. And we still have the junction edge. And first just plot the PE0, that's here. And also similarly, this is a saturation. So that means the base emitter is a forward. So we can already expect like in this way. This is a forward, so it's very similar like in this case. But right now, we also have the forward in the base and collector here. So we have here that's NBX. Because right now this is a 4 volt, so that means the concentration here cannot be 0, which will be even higher than the NB0, because right now this is a 4 volt. And also this is a 4 volt, so we will have the clock like in this way. To have a little bit precise, this should be drawn in like here. This is our NBX. Yeah, so which will be similar to this drawing. Okay, so the next we should continue to draw under the case of the cutoff. So the cutoff is both reverse bias in the BE and BC. So in this case, still the same. We have the emitter, we have base, we have a collector, and these are N plus, P plus, N here. And the cutoff, which is drawing, is very much simple. So we have the P0, PNB0, and PC0. And because the cutoff is both reverse bias here and reverse bias here, so that means the concentration here must be 0. So that's a PX prime. And also, we need to both 0, 0, but in the middle still will be able to back to the NB0. So that will be look like in this case. And also in here, this is reverse bias. So this point will still be the 0 here. So that's a case under the cutoff which BE and BC are reverse bias. And the last one is inverse active. So the inverse active just exactly opposite compared to the forward active. So we have the E, B, C. So right now our BC junction is a forward bias. So we start to have the here, and then we're back to PC0. And also in this case, we're starting from here, but now because the BE is a reverse bias, So that must be back to the 0 at this point. And also this is a reverse bias. So therefore, we can expect the PE is shown in here. Okay, so these are the 4 different modes under the different bias, reverse or forward for the each PN junction. Of course, the most important operations mode for the bipolar, which will be the forward active operation mode. So as already said that at this mode, the base emitter PN junction is forward bias. And the base collector PN junction is a reverse bias. And therefore, we can also understand the carrier transport from the band diagram. This is a band diagram under 0 bias. Right now, we have forward bias here. So forward bias means that the barrier is reduced. So the barrier reduced means the electron can start to flow from the left to the right. And rise reach to this region is under reverse bias. But the reverse bias means that we have the high electric field at here, so the carrier can be accelerated due to this high electric field. So that's why under the forward active mode, we expect there's a current can be flow in our BJT. So one thing we can understand from the band diagram, or we can also understand from the minority carrier distribution as shown in here. And this graph is also relatively complicated here. So the base emitter PN junction is forward bias, and therefore electrons from emitters are injected across the BE junction. So that means because this is a forward bias, so the carrier's electron can start to flow from the left to the right here. And these inject electron created an excess concentration. Because right now, this is electrons. Once electron flow to the base region, and the base region is mainly dominated by the hole. So electrons in this region is become like excess concentrations here. So, and also this junction is reverse bias. So the base collector p-n junction is reverse bias. So the minority carrier electron concentration at the edge of the BC junction is ideally 0. This should be ideally 0 at here. And this actually creates a very large concentration gradient. So you can see now we have electrons moving from the emitter to the base. And once the electron in the base is become like excess concentration. But we also have force to be ideal 0 at this point. And therefore we have very strong concentration gradient. And this strong concentration gradient will create the diffusion current here. So the large gradient in the electron concentration means that electrons injected from emitter will diffuse. Will diffuse across the base region into the BC space charge region. So now the first of all, forward bias, so the electrons can flow from emitter to base. And afterwards, because there's a diffusion, so the electron can start to move it due to this diffusion and in the end reach to the BC space charge region. And right now the last step is that because the high electric field here, so this charge will be swept by the electric field and to the collector side. So the electric field will sweep the electrons into the collector. In the end, we start to have the current flow here. So that's why we can have the current flow in the BJT here. So again, just try to illustrate. First of all, this is forward. So the electrons can start to overcome this barrier and flow to the P base region. And because this is reverse bias, and this needs to be 0, and therefore we have very strong concentration gradient. And strong concentration gradient will create the diffusion into the edge of the space charge region as shown here. Right now, this is under the reverse bias, and therefore we will have very strong electric field. So the electron right now will be swept by the electric field into the collector side, and in the end, it's become like the current you will measure in the collector side here. Although this graph is rather complicated because we use a concept of minority carrier, which not very often used in the last several classes. But this operation is very similar to the MOSFET. So again, let's try to look at the MOSFET. So we have the N plus, we have N plus, and we have the P substrate, right? So if we try to look a little bit zooming inside the MOSFET, you will find out that this region is NPN, which is exactly the same like this thing. So ideally, the knowledge for the operation for the MOSFET should be able consistent with knowledge in the BJT. How this similarity can be observed also can be shown in here. So as you know, once we apply the VD bias increase here, the first thing in the drain side is we will start to see the extension of the reverse bias. So now the reverse bias we're seeing will create the extension of the depletion region, right? So that's like in this way. So this one is very similar to this because this is also the reverse PN junction. So we have reverse PN junction here. And as you know, there's a moment once we apply the gate bias, but our VD is larger enough. Actually, our channel is become this way, right? That's already mentioned before. The channel will be formed because right now your drain voltage, your VGD is smaller than VTH, so your channel will be moving from the drain side to the source side. And in this case, how the carrier flow from the source to the drain, which are the first one, the carrier electron will overcome this PN junction and flow to the P substrate and start to diffuse into this region. And then in the end, the carrier can be swept by this reverse PN junction due to the electric field. So now you see, actually the operation for the MOSFET in this condition is exactly similar like in this one, because first of all, we still have the PNP in here. No, we have NPN. Sorry, this is NPN. So that's the NPN here. And also under the large drain bias, we have the extension of reverse bias. Extension of depletion region is the same one like here. So we expect there's a high electric field in this region. And also, once the electrons start to flow into this region and actually become the excess carrier concentration in the P sub, just like in the case of here. And it needs to be the zero concentration at this age. So you will start to see the carrier is diffused in this region, in the channel, in the MOSFET, which is exactly the same like here. So once the electron moving at this point, which is exactly like here, and how this electron be able to transport to the drain, that's because we have a high electric field. So the same thing is also happen in the BJT. So in general, you will find out that once you've completed all the lecture in the end, you found all the physics actually is pretty like makes sense and are very consistent. So what they are talking about is always the same things. Okay, so the rest of part, so the rest will be still the calculation. So I think we will stop the class at here, and then we will start to distribute back the midterm questions.